Welcome to another journey through the cosmos. Tonight I'll be telling you the story of reality itself, layer by layer, from the world you see with your eyes to the deepest structures of existence. But before we begin, let me tell you what to expect. This video is designed to help you fall asleep peacefully. You'll hear my voice guiding you through the fascinating layers of reality, from the human scale to the quantum realm and beyond. And then, once the story ends, you'll hear brown noise for the rest of the night. Brown noise is a deep, low-frequency sound that helps mask background sounds and keeps you in deep sleep throughout the night. So get comfortable, close your eyes, and let's begin our journey through the layers of reality. Right now, at this very moment, you exist in multiple realities at once. There's the reality you can see and touch, the world of solid objects and familiar spaces. But beneath that surface, and beyond it and woven through it, are layers upon layers of existence that you never perceive directly. You're like someone standing on the shore of an ocean, seeing only the surface, while vast depths extend below, unseen and mostly unknown. Tonight, we're going to peel back those layers one by one and discover the hidden architecture of everything that is. Close your eyes, take a deep breath, and prepare to see reality as you've never seen it before. Let's begin with the most familiar layer, the one you know best. This is the human scale, the layer of reality where you spend your entire conscious life. It's the world of chairs and tables, of rooms and buildings, of trees and mountains and oceans. Everything here seems solid, permanent, straightforward. You can reach out and touch things. You can see colors and shapes. You can hear sounds and feel textures. This layer has rules that make sense to you because you evolved to understand them. Objects fall when you drop them. Water flows downhill. The sun rises in the east and sets in the west. But here's something to consider as you lie here in the darkness. This familiar layer, the one that seems like the real world, is actually just one thin slice of existence. It's the layer that natural selection shaped your senses to perceive, because perceiving it helped your ancestors survive and reproduce. You can see objects that are roughly the size of your hand or larger, because those are the objects you needed to interact with to survive. You can't see individual atoms even though they're everywhere around you and inside you, because there was no evolutionary advantage to seeing atoms. Your ancestors didn't need to perceive atomic structure to find food, avoid predators, or raise children. Think about what this means. The reality you experience every day, the world you think of as the complete picture, is actually heavily filtered and limited. It's like living your entire life inside a house with tinted windows, never realizing that the colors you see aren't the true colors of the world outside. Your senses evolved to show you a useful picture of reality, not a complete one. They show you what you need to see to survive, nothing more. And yet, despite its limitations, this human-scale reality contains everything meaningful to you. Every conversation you've had, every sunrise you've watched, every meal you've enjoyed, every person you've loved, all of it happened here, in this one narrow band of perceptible existence. There's something profound about that. The entire drama of human life, all of history, all of art and music and literature and science, all the wars and peace treaties and revolutions and quiet moments of tenderness, all of it unfolds in this thin layer of the cosmic spectrum that your senses can detect. So let's pause here for a moment and appreciate this layer before we move beyond it. Feel the bed beneath you, solid and real. The mattress supporting your weight, the pillow cradling your head, the blanket warming you. These simple objects, these everyday things, are part of the human-scale reality. They're made of atoms, yes, which we'll explore later, but at this scale they behave as solid, dependable objects. Hear the quiet sounds around you. Maybe the hum of distant traffic, or the whisper of air through a vent, or the settling of the house as it cools in the night. These sounds travel as waves through the air, vibrating your eardrum, interpreted by your brain as the familiar acoustic landscape of your environment. This is your reality, the world you know. Hold it in your mind as we prepare to descend deeper and ascend higher, to peel back the surface and see what lies beneath and beyond. Because every other layer we explore tonight is connected to this one, supports this one, or emerges from this one. The human scale is special not because it's more real than other scales, but because it's where you live, where consciousness like yours exists and experiences existence. Now, let's shift our perspective and move to the next layer, one that's still somewhat familiar, but begins to reveal processes and structures too large or too slow to perceive in daily life. This is the planetary layer, the scale of Earth as a whole, where we see our world not as a flat surface we stand on, but as a sphere of rock and metal and water suspended in space, a complex system with its own dynamics and rhythms. From space, Earth looks deceptively peaceful, a perfect blue and white sphere, serene against the black void. But that appearance conceals extraordinary activity. The planet beneath your feet is in constant motion, though that motion is too slow for you to feel directly. The solid ground you think of as permanent and stable is actually floating on an ocean of partially molten rock called the mantle. The crust, the thin outer shell that includes the continents and ocean floors, is broken into massive pieces called tectonic plates, and these plates drift across the planet's surface at about the speed your fingernails grow. Over millions of years, these plates collide and separate and slide past each other, creating mountains, opening ocean basins, generating earthquakes and volcanic eruptions. The Himalayas are still rising, pushed upward by the collision of the Indian plate with the Eurasian plate, a collision that's been ongoing for tens of millions of years. The Atlantic Ocean is widening as the Americas drift away from Europe and Africa at a rate of a few centimeters per year. The Pacific Ocean is shrinking as the plates around its rim are pushed beneath neighboring plates in a process called subduction. This constant recycling of Earth's surface, this endless dance of tectonic plates, has shaped the planet's geography and influenced its climate throughout its 4.5 billion year history. It's also crucial for life because plate tectonics helps regulate the amount of carbon dioxide in the atmosphere, which affects global temperature. When continents collide and form mountains, those mountains are eroded by rain and wind, and the chemical weathering of rocks removes carbon dioxide from the atmosphere. When volcanoes erupt at subduction zones, they release carbon dioxide back into the atmosphere. This cycle helps keep Earth's temperature within the range where liquid water can exist, which is essential for life as we know it. Above the solid surface, the atmosphere is in constant motion too. From your perspective on the ground, the air might seem still, but seen from space, the atmosphere reveals itself as a churning sea of winds and storms. Vast rivers of air called jet streams circle the planet at high altitudes, carrying weather systems from west to east. Hurricanes and typhoons, massive rotating storms powered by warm ocean water, form in the tropics and can release as much energy as hundreds of nuclear bombs. Even on a calm day, air is moving, rising in some places and sinking in others, creating the invisible patterns of high and low pressure that determine whether you see sunshine or rain. And then there's the magnetosphere, perhaps the most invisible and yet one of the most important features of the planetary layer. Deep inside Earth, the outer core, a layer of liquid iron about 2,000 kilometers thick, is in constant turbulent motion. This motion generates electrical currents, and those currents create a magnetic field that extends far out into space, forming a protective bubble around the planet called the magnetosphere. You can't see the magnetosphere. You can't feel it as you go about your day, but it's there, and it's essential. The sun constantly ejects a stream of charged particles called the solar wind, and without the magnetosphere, these particles would strip away Earth's atmosphere over time, the way they've stripped away most of Mars' atmosphere over billions of years. The magnetosphere deflects most of these particles, channeling them around Earth. Some particles do manage to slip through near the magnetic poles, and when they collide with atoms in the upper atmosphere, they create the shimmering curtains of light called auroras, the northern and southern lights. Think about that for a moment as you rest here. Right now, invisible to you, the magnetosphere surrounds the entire planet, flexing and rippling as it interacts with the solar wind, protecting you and every other living thing from radiation that would otherwise make the surface uninhabitable. This protective shield has been operating for billions of years, maintained automatically by the churning iron in Earth's core, asking nothing of you, expecting nothing in return, simply doing what physics demands it must do. The planetary layer is a layer of systems and cycles, of processes too vast and too slow to perceive directly, but absolutely fundamental to your existence. The water cycle, endlessly moving water from ocean to atmosphere to land and back again. The rock cycle, slowly transforming one type of rock into another through heat and pressure and weathering. The carbon cycle, moving carbon between atmosphere and oceans and living things and rocks. These cycles have been operating for billions of years, maintaining conditions suitable for life, creating the stable environment in which evolution could occur and complexity could increase. And you're part of these cycles, even if you never think about it. The water in your body has been through the water cycle countless times, falling as rain, flowing in rivers, evaporating from oceans, condensing in clouds. The carbon atoms in your body were in the atmosphere as carbon dioxide until recently absorbed by plants through photosynthesis, incorporated into organic molecules, and then consumed by you or by animals you ate. When you exhale, you release carbon dioxide back into the atmosphere, where it will eventually be absorbed by another plant, continuing the cycle. You're not separate from Earth's systems. You're woven into them, sustained by them, part of them. Now let's move outward from Earth to the next layer, the solar system layer, where we see our planet not as the center of everything, but as one world among many, all orbiting the sun, all bound together by gravity in an intricate cosmic dance that's been choreographed by physics for 4.5 billion years. At the center of this dance is the sun, and the sun is extraordinary. It's not just a bright light in the sky. It's a star, a sphere of plasma about 110 times Earth's diameter, containing more than 99% of all the mass in the solar system. Deep in the sun's core, where temperature and pressure are extreme beyond anything we can easily imagine, nuclear fusion occurs. Every second, the sun converts about 600 million tons of hydrogen into helium, and in the process, about 4 million tons of mass are converted into pure energy, according to Einstein's equation, E equals mc squared. That energy doesn't escape the sun instantly. Photons created in the core bounce randomly from atom to atom in the dense plasma of the sun's interior, taking thousands or even hundreds of thousands of years to work their way out to the surface. But once they reach the surface, they stream away at the speed of light, and just 8 minutes later, some of them reach Earth, warming your skin when you step outside, powering photosynthesis in plants, driving weather systems and ocean currents. The warmth of sunlight you feel on your face is energy that was created deep in the sun's core, perhaps 50,000 years ago, when your ancestors were still living in small hunter-gatherer groups and the last ice age hadn't yet ended. The sun doesn't just provide light and heat. It fills the entire solar system with a stream of charged particles called the solar wind, flowing outward at hundreds of kilometers per second. This wind creates a bubble called the heliosphere that extends far beyond the orbit of Pluto, far beyond the Kuiper Belt, where countless icy bodies orbit in the darkness. The heliosphere protects the solar system from the harsh radiation and cosmic rays of interstellar space. We live inside this bubble, inside the sun's domain, in a region of space shaped by our star. Around the sun, 8 planets trace their ancient orbits, some close and fast, others distant and slow. Mercury, the innermost planet, whips around the sun every 88 days. Baked by intense solar radiation, its cratered surface, remembering billions of years of asteroid impacts. Venus, shrouded in thick clouds of sulfuric acid, spins slowly backward, taking longer to rotate once on its axis than it does to orbit the sun. Its atmosphere is so dense and its greenhouse effect so extreme that surface temperatures reach 470 degrees Celsius, hot enough to melt lead. Earth orbits third from the sun in what's called the habitable zone, where temperatures allow liquid water to exist on the surface. This isn't just lucky chance. Earth's distance from the sun, its size, its composition, the presence of its large moon, all of these factors work together to create conditions suitable for life. If Earth were slightly closer to the sun, it might have suffered a runaway greenhouse effect like Venus. Slightly farther out, and it might have frozen like Mars, which orbits forth from the sun, a cold desert world with a thin atmosphere, its surface carved with the dry channels of rivers that flowed billions of years ago when Mars was warmer and wetter. Beyond Mars lies the asteroid belt, a region where millions of rocky bodies orbit, remnants from the early solar system that never coalesced into a planet, probably because Jupiter's gravity prevented them from doing so. And Jupiter itself, the giant planet, orbits beyond the asteroid belt, so massive that it contains more than twice the mass of all other planets combined. Jupiter is a world of storms and flowing bands of clouds, with a magnetic field 20,000 times stronger than Earth's, and a retinue of at least 79 moons, including 4 large ones that Galileo discovered in 1610, providing crucial evidence that not everything orbits Earth. Saturn orbits farther out, famous for its magnificent ring system, though all 4 giant planets have rings to some degree. Saturn's rings are the most spectacular, stretching hundreds of thousands of kilometers across space, but only about 10 meters thick in most places, made of countless particles of ice and rock, each one orbiting Saturn independently. The rings are dynamic, constantly evolving, shepherded by small moons, resonating with larger moons, creating intricate patterns and structures that have fascinated astronomers for centuries. Uranus and Neptune, the ice giants, orbit in the outer reaches of the solar system, cold and mysterious worlds that we visited only once each with the Voyager 2 spacecraft in the 1980s. Uranus has the strange distinction of being tipped over on its side, its axis of rotation nearly in the plane of its orbit rather than perpendicular to it, possibly because of a massive collision early in solar system history. Neptune, the farthest major planet, has the fastest winds in the solar system, with storms where wind speeds reach over 2,000 kilometers per hour. All these worlds, all this structure, exists because of gravity, the fundamental force that shapes the cosmos at large scales. Gravity pulled together the cloud of gas and dust that became the solar system. Gravity ignited fusion in the sun. Gravity shaped the planets into spheres and keeps their atmospheres from drifting away. Gravity maintains the planets in their orbits, creating the elegant mathematical relationships that Kepler discovered 4 centuries ago and Newton explained with his law of universal gravitation. The solar system layer is a realm of vast distances and patient timescales. The planets move quickly from our perspective, but their orbits are so large that they take months or years or even centuries to complete one revolution around the Sun. Jupiter takes 12 years, Saturn 29 years, Neptune 165 years. So anyone alive when it was discovered in 1846 has not yet seen it complete even a single orbit. Changes happen slowly at this scale. Moons form, craters accumulate, atmospheres evolve over millions and billions of years. And yet, despite the slow pace of change, the solar system has a history, a story that began 4.5 billion years ago when a cloud of gas and dust in this region of the galaxy began to collapse under its own gravity. Most of the material fell toward the center and became the Sun. The remaining material formed a disk around the young star, and within that disk, dust grains stuck together, forming pebbles, then boulders, then planetesimals, then protoplanets, growing larger and larger through countless collisions over millions of years. Earth formed from this chaotic process, along with all the other planets. Every rock and grain of sand on Earth, every drop of water in the oceans, every atom in your body was once part of that primordial disk of dust orbiting the young Sun. The solar system is your extended home, the cosmic neighborhood you're part of, the family of worlds that share your origin story. Let's journey outward again now, beyond the solar system to the stellar layer, the scale of stars themselves, thousands and millions and billions of them, scattered through the vast volume of our galaxy, like islands in an immense ocean of space. If you could see the galaxy from outside, from some impossible vantage point far beyond its edge, you'd see a majestic spiral, a great pinwheel of stars rotating slowly around a bright central bulge. This is the Milky Way, our home galaxy, containing somewhere between 200 and 400 billion stars, spread across a disk about 100,000 light-years in diameter. The disk is thin compared to its width, only about 1,000 light-years thick in the region where the Sun orbits, which is about halfway out from the center to the edge. Our sun, that massive ball of plasma that dominates our sky and powers all life on Earth, is just one ordinary star among that vast multitude. Not a special star, not particularly large or bright, just an average yellow dwarf star in a quiet neighborhood, orbiting the galactic center at about 230 kilometers per second, taking about 230 million years to complete one orbit. The last time the sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. Look up at the night sky on a clear, dark night, far from city lights. Every point of light you see is a star, every one a member of our galaxy, a fellow traveler through space. Most of the stars visible to your naked eye are within a few thousand light years of Earth, relatively close neighbors in galactic terms. The most distant stars you can see without a telescope are about 15,000 light years away, which means the light entering your eyes left those stars 15,000 years ago, when human civilization was just beginning, when agriculture had not yet been invented, when the last ice age had not yet fully ended. Stars are not eternal, even though they seem unchanging from a human perspective. They're born, they live, and they die. A star's life begins in a molecular cloud, a vast region of gas and dust floating in space. When part of such a cloud collapses under its own gravity, perhaps triggered by the shock wave from a nearby supernova, the collapsing material heats up as gravitational potential energy is converted to thermal energy. If enough material gathers and the core becomes hot enough, nuclear fusion ignites. A star is born. The star then enters the main sequence, the stable period that makes up most of a star's life, during which it fuses hydrogen into helium in its core. Our sun has been on the main sequence for about 4.5 billion years and will remain there for another 5 billion or so. But the main sequence doesn't last forever. Eventually, the hydrogen in the core runs out. What happens next depends on the star's mass. For stars like the sun, the core contracts and heats up, and the outer layers expand dramatically. The star becomes a red giant, perhaps swelling to 100 times its previous size. In about 5 billion years, our sun will become a red giant, expanding past the orbit of Mercury, possibly past Venus, maybe even to Earth's orbit. The habitable zone will move outward, and Earth, if it survives, will become a charred, lifeless cinder orbiting far inside the star's outer envelope. Eventually, the red giant sheds its outer layers in a series of pulses, creating a beautiful planetary nebula, a shell of glowing gas expanding into space. What remains is the hot, dense core, a white dwarf star about the size of Earth but containing about half the sun's mass. White dwarfs don't undergo fusion. They simply cool slowly over trillions of years, gradually fading from white to yellow to red to eventually black, though the universe isn't old enough yet for any white dwarfs to have cooled completely to black dwarfs. Massive stars, those with more than about 8 times the sun's mass, have more dramatic endings. They burn through their fuel much faster, living only millions of years instead of billions. When they exhaust the hydrogen in their cores, they begin fusing heavier elements, helium into carbon and oxygen, carbon into neon and magnesium, all the way up to iron. But iron can't be fused to release energy. When the core becomes predominantly iron, fusion stops, and without the outward pressure from fusion, the core collapses catastrophically. The collapse happens in less than a second, and the rebound generates a shock wave that blows the star apart in a supernova. one of the most energetic events in the universe. For a few weeks, the supernova can shine as brightly as an entire galaxy, outshining all the billions of stars in its host galaxy combined. The explosion scatters the star's material into space, enriching the interstellar medium with the heavy elements created during the star's life and in the explosion itself. These heavy elements, everything heavier than helium, were created inside stars. The carbon in your body, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, all of it was forged in the nuclear furnaces of stars and scattered into space when those stars died. You are, quite literally, made of stardust, made of atoms that were cooked up in stars that lived and died billions of years ago, before the sun and earth even existed. Some massive stars, when they explode, leave behind a neutron star, an object about 20 kilometers in diameter, but containing more mass than the sun. Neutron stars are so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. They have the strongest magnetic fields in the universe, and some rotate rapidly, hundreds of times per second, emitting beams of radiation that sweep across space like lighthouse beams. We detect these as pulsars, cosmic clocks that keep time with extraordinary precision. The most massive stars, when they die, leave behind black holes, regions where gravity has become so strong that nothing, not even light, can escape. Black holes are perhaps the strangest objects in the universe, places where space and time are warped so severely that our usual concepts break down. Cross the event horizon of a black hole, the point of no return, and you can never come back. All paths lead inward toward the singularity at the center, where density becomes infinite and our current theories of physics fail to describe what happens. The stellar layer is a layer of creation and destruction, of birth and death on cosmic scales. It's where elements are made, where the building blocks of planets and life are forged. It's where matter is transformed, where hydrogen, the simplest and most abundant element in the universe, is gradually converted into heavier elements through fusion, enriching the cosmos with a diversity of atoms that makes chemistry and biology possible. And the stellar layer is vast. The stars visible to you on a clear night are only the nearest ones, only a tiny fraction of the stars in the galaxy. Most stars are too far away for you to see without a telescope, and each of those stars is a sun in its own right, potentially with planets orbiting it, perhaps even planets with life. The stellar layer is not just a backdrop for Earth. It's a vast ecosystem of matter and energy and time, and we're part of it, living on a planet orbiting one of those countless stars. Now let's expand our view even further to the galactic layer, where individual stars fade into insignificance and the basic unit becomes the galaxy itself, collections of hundreds of billions of stars moving through space together, shaped by gravity and dark matter into the grand structures we observe through telescopes. The Milky Way, our home galaxy, is a spiral galaxy, which means it has a flat disk with spiral arms winding outward from a central bulge. If you could see it from above, it would look like a cosmic whirlpool, with streams of stars and gas and dust flowing along those spiral arms. But we can't see it from above because we're inside it, embedded in one of those spiral arms about halfway from the center to the edge. And when we look toward the galactic center, we see a thick band of stars crossing the sky, the river of light that ancient peoples called the Milky Way, not knowing that it was actually our view edge on through the disk of a vast galaxy. At the center of the galaxy, hidden behind thick clouds of dust that block visible light but not infrared or radio waves, lies something remarkable and mysterious. It's a supermassive black hole, an object containing about 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. This black hole, called Sagittarius A star, is the gravitational anchor of the galaxy, the point around which all those hundreds of billions of stars orbit. We can't see the black hole directly because black holes by definition don't emit light, but we can see its effects. Stars very close to the galactic center orbit it at tremendous speeds, taking just years or even months to complete their orbits despite being light years away from the black hole. By tracking the motion of these stars over time, astronomers have been able to calculate the mass and position of the central black hole with great precision. In 2020, the team that made these measurements was awarded the Nobel Prize in Physics. The Milky Way isn't alone in space. It's part of a small cluster of galaxies called the Local Group, which includes about 80 galaxies in total. Most of these are small dwarf galaxies, containing only millions or billions of stars, but there are 3 large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda is the nearest large galaxy to us, about 2.5 million light-years away, and it's actually slightly larger than the Milky Way, containing perhaps 1 trillion stars. Andromeda and the Milky Way are moving toward each other at about 120 kilometers per second, drawn together by their mutual gravity. In about 4.5 billion years they will collide. Don't imagine a violent crash, though. Galaxies are mostly empty space, and when 2 galaxies merge, their stars rarely collide with each other directly. Instead, the galaxies pass through each other, their gravity pulling them back together for a second pass, and then a third, each pass further disrupting their structure, until after about 1 billion years they settle into a single merged galaxy, probably an elliptical galaxy, which is what happens when spiral galaxies collide. By the time the Milky Way and Andromeda merge, the Sun will already be entering its red giant phase, and Earth will be uninhabitable, if it still exists at all. Any civilizations that survive to witness the collision will see a remarkable sight in their night sky. The 2 galaxies distorted by tidal forces, streams of stars pulled out into long filaments, regions of intense star formation where clouds of gas are compressed by the collision. It will be one of the most dramatic astronomical events possible, played out over millions of years, visible to any observers patient enough to watch. Beyond the Local Group, the universe is filled with galaxies, hundreds of billions of them, perhaps even trillions. Some are spirals like the Milky Way and Andromeda. Others are elliptical, shaped like footballs or eggs, with no disk structure, just a smooth distribution of old stars. Still others are irregular, chaotic collections of stars with no clear organization, often the result of past collisions and mergers. Galaxies aren't evenly distributed through space. They cluster together, drawn by their mutual gravity, forming groups and clusters and superclusters. The Local Group is part of the Virgo supercluster, a large structure containing thousands of galaxies spread across about 110 million light-years. And the Virgo supercluster is itself just one part of an even larger structure called Laniakea, which contains about 100,000 galaxies. On the largest scales, the universe reveals a structure that's been described as a cosmic web. Dense filaments of galaxies stretch across hundreds of millions of light-years, connecting massive nodes where galaxy clusters gather. Between these filaments are vast voids, regions where very few galaxies exist, empty spaces that can span hundreds of millions of light years. This cosmic web formed gradually as gravity amplified tiny density fluctuations in the early universe, pulling matter together into ever larger structures. The galactic layer is also where we encounter one of the greatest mysteries in modern physics: dark matter. When astronomers measure how fast galaxies rotate, they find something strange. The outer parts of galaxies are moving faster than they should based on the visible matter they contain. According to Newton's laws and Einstein's general relativity, the gravity of all the stars, gas, and dust in a galaxy should produce a certain pattern of rotation, with outer regions moving slower than inner regions. But that's not what we observe. Outer regions are moving almost as fast as inner regions, which means there must be additional mass we can't see, mass that provides extra gravity. This invisible mass is dark matter, and it makes up about 85% of all the matter in the universe. We don't know what dark matter is made of. It's not made of atoms like ordinary matter. It doesn't emit, absorb, or reflect light, which is why we call it dark. It interacts with ordinary matter only through gravity, making it extraordinarily difficult to detect directly. But its gravitational effects are unmistakable. Dark matter forms vast halos around galaxies, extending far beyond the visible stars, providing the gravity that holds galaxies together and shapes their rotation. Finding out what dark matter actually is remains one of the great challenges in physics. Physicists have built sensitive detectors deep underground, hoping to catch rare interactions between dark matter particles and ordinary matter. So far, these searches have come up empty, which tells us that if dark matter is made of particles, those particles interact extraordinarily weakly with ordinary matter. The mystery remains unsolved, a reminder that even with all our technology and knowledge, the universe can still surprise us with phenomena we don't yet understand. The galactic layer is where individual human lives become almost incomprehensibly small. A human lifetime is about 80 years. A galactic rotation takes about 230 million years. You would need nearly 3 million human lifetimes to watch the galaxy complete one orbit. And yet, you're part of this vast structure, living on a planet orbiting a star that's just one tiny component of a system containing hundreds of billions of stars. The scale is humbling, but it's also awe-inspiring. You're part of something vast and ancient and beautiful, something that was here long before you and will be here long after you're gone. Now let's expand our perspective to the ultimate scale, the cosmic layer, where we see not just our galaxy but the entire observable universe, the vast expanse of space containing billions of galaxies, stretching as far as we can see in every direction, all of it evolving according to the laws of physics, all of it connected by the same fundamental forces. The universe is expanding. This is one of the most important discoveries in the history of science, made in the 1920s when astronomer Edwin Hubble measured the distances to nearby galaxies and found that they were moving away from us. And the farther away they were, the faster they were receding. This pattern is exactly what you'd expect if space itself is stretching, carrying galaxies apart like raisins in a rising loaf of bread. The expansion of the universe tells us something profound. The universe had a beginning. If we run the expansion backward in time, we find that the universe was smaller in the past, denser and hotter. Go back far enough, and the universe was compressed into a state of unimaginable density and temperature. This was the Big Bang, the event that marks the beginning of the universe as we know it, about 13.8 billion years ago. The Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no center, no edge, no point from which everything exploded outward. Every point in space was part of that initial singularity, and as space expanded, every point moved away from every other point. If you could watch the universe evolving over time, you wouldn't see galaxies flying away from a central point. You'd see them moving away from each other in all directions, with each galaxy seeing every other galaxy receding from it. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation, growing from smaller than an atom to larger than a galaxy in less than a billionth of a trillionth of a second. This rapid expansion smoothed out the universe, making it very uniform on large scales, and also generated the tiny quantum fluctuations that would later be amplified by gravity to become the seeds of all cosmic structure. As the universe expanded, it cooled. In the first few minutes, when the temperature was still billions of degrees, protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium, with trace amounts of deuterium, helium-3, and lithium. But it took about 380,000 years for the universe to cool enough for electrons to combine with nuclei and form the first neutral atoms. When that happened, the universe became transparent for the first time, and light could travel freely through space. That light is still around today. As the universe has expanded, the light has been stretched to longer wavelengths, shifted from visible light to infrared to microwave radiation. We detect it as the cosmic microwave background, a faint glow of radio waves coming from every direction in the sky, the oldest light in the universe, the afterglow of the Big Bang itself. By measuring tiny variations in the temperature of this radiation, astronomers have learned an enormous amount about the early universe, about its composition, its age, its geometry, and the processes that shaped it. For hundreds of millions of years after the cosmic microwave background was emitted, the universe was dark. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium floating through space, slowly collapsing under their own gravity. This period is called the Cosmic Dark Ages, and it lasted until the first stars ignited, ending the darkness and beginning the process of creating heavier elements. Those first stars were probably very massive and very short-lived, and they've all died by now, their material scattered into space and recycled into later generations of stars. Each subsequent generation of stars has had slightly more heavy elements, because each generation inherits the products of previous generations. The Sun is a third-generation star or later, containing elements that could only have been made in earlier stars that lived and died before the solar system formed. Galaxies formed as these early stars clustered together, drawn by gravity, merging and colliding and growing over billions of years. Our own galaxy is still growing, still pulling in smaller galaxies that wander too close. The Magellanic Clouds, two small irregular galaxies visible from the southern hemisphere, are satellites of the Milky Way orbiting our galaxy and gradually being torn apart by its gravity. Eventually, they'll merge with the Milky Way completely. The expansion of the universe has an interesting property. The more distant a galaxy is, the faster it appears to be receding from us. This is described by Hubble's law. Velocity equals the Hubble constant times distance. The Hubble constant, about 70 kilometers per second per megaparsec, tells us the rate of expansion. For every megaparsec, about 3.3 million light-years of distance, the recession velocity increases by about 70 kilometers per second. This means that sufficiently distant galaxies are receding from us faster than the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies with it, and there's no limit on how fast space can expand. The consequence is that there's a limit to how far we can see. Light from galaxies beyond a certain distance, about 46 billion light-years in all directions, can never reach us because the space between us and them is expanding faster than light can cross it. This defines the observable universe, the region of space from which light has had time to reach us since the Big Bang. Beyond the observable universe, space presumably continues, perhaps infinitely, perhaps containing infinitely many galaxies we can never observe. We don't know if the universe is infinite or finite. If it's finite, it might curve back on itself like the surface of a sphere, so that if you traveled far enough in one direction, you'd eventually come back to where you started. But measurements of the cosmic microwave background suggest that if there is any curvature, it's extremely small, and the universe is very close to flat. Here's something even more mysterious. About 25 years ago, astronomers discovered that the expansion of the universe is accelerating. For most of cosmic history, the expansion was slowing down, as you'd expect, because the gravity of all the matter in the universe pulls everything together, resisting the expansion. But about 5 billion years ago, the expansion started speeding up again. Something is pushing the universe apart, causing the expansion to accelerate, and we don't know what it is. We call it dark energy, and it makes up about 68% of the total energy content of the universe. Dark matter, that mysterious invisible mass, makes up about 27%. Ordinary matter, the stuff you're made of, the stuff stars and planets are made of, makes up only about 5%. We live in a universe dominated by things we don't understand. Dark energy might be a property of space itself, a kind of intrinsic energy that every cubic meter of space possesses. As space expands, creating more volume, the total amount of dark energy increases, and this drives the accelerating expansion. Or dark energy might be something else, some new field or force we haven't discovered yet. What we know is that if dark energy continues to dominate, the universe will keep expanding faster and faster, and eventually, in trillions of years, galaxies will be so far apart that beings living in any one galaxy will only be able to see their own galaxy with nothing else visible in any direction. The observable universe will shrink, in a sense, as distant galaxies recede beyond the horizon of what can ever be observed. The cosmic layer is a layer of vast distances and deep time. It's where we see the universe not as a static backdrop, but as a dynamic, evolving system with its own history, its own future, its own grand narrative stretching from the Big Bang to whatever ultimate fate awaits. And we're part of that narrative, living in a brief moment of cosmic history when stars are shining, when galaxies are visible, when the universe is old enough to have created heavy elements, but young enough that stars still form and life can exist. Now let's reverse our journey. We've traveled outward through larger and larger scales, from the human world to the planet to the solar system to the stars and galaxies. and finally to the entire observable universe. But reality doesn't just extend outward. It extends inward too, down to smaller and smaller scales. And that's where some of the deepest mysteries and strangest phenomena lie. Let's descend now through the layer of deep time. Not a layer of space, but a layer of time itself, where we see how the universe and Earth and life have changed and evolved over billions of years. How the present moment is just one frame in a film that's been running for almost 14 billion years. The sun is about 8 light minutes away, which means you see the sun as it was 8 minutes ago. If the sun suddenly vanished, you wouldn't know for 8 minutes. The nearest stars are light years away, so you see them as they were years ago. The Andromeda galaxy is 2.5 million light years away, so the light you see from it left Andromeda when early humans were just beginning to use stone tools on Earth. The most distant galaxies visible through our most powerful telescopes are so far away that we see them as they were over 13 billion years ago, when the universe was young and those galaxies were just beginning to form. This means we can observe cosmic history directly. By looking at objects at different distances, we're seeing them at different times in the past, and we can watch how the universe has changed and evolved. We can see that galaxies in the distant past were smaller and more irregular than galaxies today. We can see that the rate of star formation has decreased over cosmic time. We can trace the history of cosmic structure from the nearly uniform distribution of matter in the early universe, visible in the cosmic microwave background, to the rich tapestry of galaxies and galaxy clusters and voids we see today. The deep time layer extends here on Earth as well. Earth's history is written in rocks, in the layers of sediment deposited over millions of years, in fossils preserved in stone, in the slow changes of landscapes and climates recorded in geological evidence. The Earth is 4.5 billion years old, formed from the same cloud of gas and dust that gave birth to the Sun and the other planets. For the first few 100 million years, Earth was a hellish place, bombarded constantly by asteroids and comets, its surface molten or at best barely solid, its atmosphere thick with water vapor and carbon dioxide and lacking in oxygen. This was the Hadean Aeon, named after Hades, the underworld in Greek mythology. No rocks from this period have survived, destroyed by subsequent geological activity, but we can infer what Earth was like from computer models and from studying meteorites, which are remnants from the same early period. Gradually, as the bombardment slowed and the surface cooled, conditions became less hostile. Liquid water appeared on the surface, forming the first oceans. And at some point, about 3.8 or 3.5 billion years ago, life emerged. We don't know how it happened. This is one of the great unsolved problems in science, the origin of life from non-living chemistry. But somehow, in those ancient oceans, or perhaps in volcanic vents on the seafloor, simple organic molecules formed and began to replicate and evolve. The first life was almost certainly very simple, single-celled organisms without even a nucleus, prokaryotes like modern bacteria. For billions of years, that's all there was. Life remained microscopic, simple, widespread, but unremarkable. And yet, even in this simple form, life was changing the planet. Some early microbes evolved photosynthesis, using energy from sunlight to convert carbon dioxide and water into sugars and oxygen. At first, the oxygen was absorbed by rocks and dissolved in oceans, but eventually, about 2.5 billion years ago, oxygen began to accumulate in the atmosphere in what's called the Great Oxidation Event. This was a catastrophe for most life at the time, because oxygen was toxic to anaerobic organisms that had evolved in an oxygen-free environment. But it was also an opportunity. Oxygen is a highly reactive molecule that can release a lot of energy when combined with other substances, and organisms that could use oxygen for respiration had access to far more energy than their anaerobic cousins. This may have been crucial for the later evolution of complex, energy-hungry organisms like animals. About 2 billion years ago, something remarkable happened. Some cells began to engulf other cells without digesting them, creating a symbiotic relationship. The engulfed cells became organelles, specialized structures inside the host cell. This process, called endosymbiosis, gave rise to eukaryotic cells, cells with a nucleus and other internal structures. Mitochondria, the powerhouses of eukaryotic cells, were once free-living bacteria that were incorporated into another cell and became permanent residents. Chloroplasts in plant cells, which perform photosynthesis, have a similar origin. Eukaryotic cells are the basis for all complex life. All animals, plants, fungi, and protists are eukaryotes. But it took a long time for eukaryotes to develop into multicellular organisms. For about 1 billion years after eukaryotic cells first appeared, life remained mostly single-celled. Then, about 600 million years ago, the first truly multicellular organisms evolved, simple animals that lived in the oceans. And then, about 540 million years ago, something extraordinary happened. Life exploded in diversity and complexity in what's called the Cambrian explosion. Over a relatively brief period of perhaps 20 or 30 million years, most of the major animal body plans appeared in the fossil record. Suddenly, the oceans were filled with a vast array of different creatures. Arthropods like trilobites, early fish, mollusks, worms, strange animals that don't fit into any modern category. The reasons for this explosion of diversity are still debated, but it may have been triggered by rising oxygen levels, by the evolution of predation, creating an evolutionary arms race, or by genetic innovations that allowed for more complex body structures. Since the Cambrian, life has continued to evolve and diversify, moving on to land, developing new forms and strategies, surviving multiple mass extinctions. The dinosaurs ruled for over 160 million years, and then went extinct 65 million years ago when an asteroid about 10 kilometers in diameter hit Earth near what is now the Yucatan Peninsula in Mexico. The impact threw massive amounts of dust and debris into the atmosphere, blocking sunlight, causing temperatures to plummet, and disrupting ecosystems worldwide. About 75% of all species went extinct, but life recovered, as it always has after mass extinctions. Mammals, which had been small and inconspicuous while the dinosaurs dominated, suddenly had room to expand and diversify. Over tens of millions of years, mammals evolved into the bewildering variety we see today, from tiny shrews to enormous whales. Primates evolved, developing larger brains, complex social structures, and eventually the capacity for language and abstract thought. The first humans appeared about 300,000 years ago in Africa, and over time they spread across the globe. All of human history, from the first civilizations to the present day, is contained in just the last 10,000 years or so, a tiny fraction of Earth's history, a blink of an eye in deep time. The pyramids of Egypt, ancient as they seem to us, were built less than 5,000 years ago. From Earth's perspective, that was yesterday. The deep time layer reminds us of our place in the grand sweep of cosmic and terrestrial history. We're latecomers, living in an old universe on an ancient planet. The atoms in our bodies are even older than Earth, forged in stars that lived and died before the sun was born. We're part of a story that's been unfolding for almost 14 billion years, and we're only conscious of it for the tiniest sliver of that time. Now, let's descend to the quantum layer, where the familiar rules of classical physics break down and reality becomes strange, probabilistic, and fundamentally uncertain. This is the realm of atoms and subatomic particles, where the wave-particle duality of matter becomes apparent, where objects can be in multiple states at once, where the very act of observation affects what is being observed. Everything you see and touch is made of atoms, tiny structures consisting of a nucleus surrounded by electrons. The nucleus contains protons, which have a positive electric charge, and neutrons, which have no charge. Electrons, which have a negative charge, orbit the nucleus, though orbit isn't quite the right word. In quantum mechanics, electrons don't follow definite paths like planets orbiting the sun. Instead, they exist in orbitals, regions of space where they're likely to be found, described by quantum wave functions that give probabilities rather than certainties. This uncertainty isn't just a limitation of our measuring instruments. It's a fundamental feature of reality at quantum scales. The Heisenberg uncertainty principle tells us that certain pairs of properties, like position and momentum, can't both be known precisely at the same time. The more accurately you measure an electron's position, the less accurately you can know its momentum, and vice versa. This isn't because measuring disturbs the electron, though that can happen. It's because at the quantum level, particles simply don't have definite values for both properties simultaneously. Even stranger is the concept of superposition. A quantum particle can exist in a superposition of multiple states at the same time. An electron can be in a superposition of being in two different places at once. A photon can be in a superposition of having two different polarizations at once. The particle isn't really in one state or the other before you measure it. It's in both states, and only when you make a measurement does it collapse into one definite state. The famous thought experiment of Schrödinger's cat illustrates this weirdness. Imagine a cat in a sealed box with a device that has a 50% chance of killing the cat. Until you open the box and observe the cat, quantum mechanics says the cat is in a superposition of being both alive and dead. Of course, this seems absurd when applied to a macroscopic object like a cat, and the question of why we don't observe such superpositions in everyday life is called the measurement problem. Different interpretations of quantum mechanics give different answers, but there's no consensus on which interpretation is correct. Quantum mechanics also features entanglement, perhaps the strangest phenomenon of all. Two particles can become entangled, meaning their properties are correlated in ways that persist even when the particles are separated by large distances. If you measure one entangled particle and find it has a particular property, you instantly know the corresponding property of the other particle, even if it's light years away. Einstein called this spooky action at a distance and thought it meant quantum mechanics must be incomplete. But experiments have confirmed that entanglement is real, though it doesn't allow faster-than-light communication because you can't control what you'll measure. At even smaller scales, we encounter quantum field theory, which describes particles not as individual objects, but as excitations of underlying fields that permeate all of space. There's an electron field, a photon field, a quark field, and so on. What we call a particle is really a ripple or vibration in one of these fields. The electromagnetic field, for example, can vibrate, and those vibrations are photons. The electron field can be excited, and those excitations are electrons. This perspective leads to a strange conclusion. Empty space, what we call the vacuum, isn't really empty. It's filled with quantum fields, and those fields are never completely still. They fluctuate constantly due to quantum uncertainty, creating virtual particles that pop into existence for brief moments and then annihilate. These quantum vacuum fluctuations have real, measurable effects. They cause the Casimir effect, where two metal plates placed very close together in a vacuum experience a slight attractive force because the vacuum between the plates has fewer modes of fluctuation than the vacuum outside. They also contribute to the anomalous magnetic moment of the electron, a property that's been measured to incredible precision and matches theoretical predictions to 13 decimal places. The quantum layer is where determinism breaks down. In classical physics, as you know the initial conditions of a system perfectly, you can predict its future behavior with perfect accuracy. But quantum mechanics is fundamentally probabilistic. The best you can do is calculate probabilities for different outcomes. You can't predict with certainty where an electron will be detected, only give odds for different locations. Einstein famously objected to this, saying, "God does not play dice with the universe, but as far as we can tell, at the quantum level, God does play dice." And yet, despite its strangeness, quantum mechanics works. It's the most successful physical theory ever developed, confirmed by countless experiments, never once contradicted by observation. It's the foundation of modern technology. Lasers, transistors, computer chips, LED lights, MRI machines, all of these depend on quantum mechanics. The device you're using to listen to this, whether it's a phone or computer, contains billions of transistors that operate according to quantum mechanical principles. Every time you use electronics, you're relying on our understanding of the quantum layer, even if you're not aware of it. Some physicists think there might be layers deeper than the quantum layer. String theory, for example, proposes that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles. An electron is a string vibrating in one way. A quark is a string vibrating in another way. String theory is elegant and mathematically beautiful, and it naturally incorporates gravity, which has been difficult to reconcile with quantum mechanics. But it requires extra dimensions, perhaps 10 or 11 dimensions total, most of which are compactified into structures too small to detect. Whether string theory is correct, we don't know. It makes few testable predictions that we can verify with current technology, and some physicists doubt whether it's science or just beautiful mathematics. But the possibility that particles are actually strings vibrating in higher dimensions is tantalizing. It would mean that the quantum layer isn't the deepest layer after all, that there's something even more fundamental underlying the particles we think of as elementary. And finally, we come to perhaps the most mysterious layer of all, the layer of consciousness, the fact that you exist as a subjective observer, experiencing reality from a particular point of view, aware of your own existence and able to contemplate these questions about the nature of reality. Consciousness is the hardest problem in all of science. We don't understand how it arises, how physical processes in a brain made of atoms following the laws of physics give rise to subjective experience, to the feeling of what it's like to be you. Your brain is just matter, about 1.4 kilograms of tissue containing roughly 86 billion neurons, each connected to thousands of others, creating a network of trillions of connections. Electrical and chemical signals flow through this network constantly, patterns of activity that somehow, in ways we don't fully understand, generate thought, emotion, perception, memory, consciousness itself. Some philosophers and scientists argue that consciousness is an emergent property, something that arises from the complex interactions of neurons but isn't reducible to those interactions, just as the wetness of water isn't a property of individual water molecules, but emerges from how they interact in large numbers. Others believe consciousness might be more fundamental, perhaps connected to quantum processes in the brain, or perhaps a basic feature of the universe that all matter possesses to some degree, with human consciousness just being a particularly complex manifestation. We don't know. Despite centuries of philosophy and decades of neuroscience, consciousness remains deeply mysterious. We can map brain activity and correlate it with conscious experiences. We can identify brain regions involved in different types of processing. We can even induce or suppress certain conscious experiences by stimulating or inhibiting specific areas of the brain. But we still can't explain why there's something it's like to be you, why your brain doesn't just process information unconsciously, but generates a rich inner world of subjective experience. Here's the profound thing: all the other layers we've discussed tonight, from the human scale to the cosmic scale, from the planetary to the quantum, all of them are known to you only through consciousness. You don't experience quantum wave functions directly. You don't see the curvature of space-time or the expansion of the universe. You don't feel the motion of tectonic plates or the rotation of the galaxy. Everything you know about reality comes filtered through your conscious experience, through sensations and perceptions and thoughts that arise in your brain. In a deep sense, consciousness is the bridge between you and everything else. It's how you access reality, how you know anything at all. And yet, of all the layers we've explored, it's the one we understand least. We can measure particles that are so small we can never see them directly. We can detect galaxies so distant their light has traveled for billions of years to reach us. But we can't explain the subjective experience happening right now in your own mind as you lie here listening to these words and contemplating the nature of existence. Perhaps consciousness will always remain somewhat mysterious. Perhaps it's the one thing that can never be fully objectified, never completely explained in terms of something else, because it's the means by which we do the explaining. Or perhaps someday we'll figure it out, and the mystery of subjective experience will join the long list of phenomena that once seemed inexplicable but are now understood. Time will tell. For now, though, just appreciate the fact that you're conscious, that you exist as an aware being capable of contemplating these questions. You're the universe becoming aware of itself, matter organized in such a way that it can wonder about matter, consciousness, pondering consciousness. And that's remarkable, however it happens, whatever the explanation turns out to be. So here we are, having journeyed through the layers of reality, From the familiar human scale outward to planets and stars and galaxies and the cosmos, and then inward and downward through deep time and quantum mechanics to the smallest scales and the deepest mysteries. And at every layer, we've found beauty and complexity, structure and pattern, things that seem impossible but are real, phenomena that challenge our intuitions but reveal the true nature of existence. You inhabit all these layers simultaneously. Your body exists at the human scale, made of cells and organs that function together to keep you alive. Those cells are made of atoms obeying quantum mechanics, and those atoms were forged in stars billions of years ago. You live on a planet shaped by geological processes operating over deep time, orbiting a star that's one of hundreds of billions in a galaxy, which is itself one of hundreds of billions of galaxies in an expanding universe that began 13.8 billion years ago. And through all of this, you have consciousness, the mysterious faculty that allows you to know and wonder about all these layers. You're not separate from reality. You're woven into it at every level, participating in all these layers at once. The matter in your body is part of the cosmic cycle of matter, created in stars, recycled through planets, destined to return to the cosmos eventually. Your consciousness is a pattern of activity in a physical brain arising from processes that connect the quantum and the biological, the material and the experiential. You're a bridge between layers, a point where reality folds back on itself and becomes aware. And now my voice is going to fade away, and you'll hear brown noise for the rest of the night. This deep, soothing sound will help mask any background noise and keep you in peaceful, uninterrupted sleep. The brown noise is like distant thunder or a waterfall, low and constant, a gentle presence that will carry you through the night. There's nothing more you need to do. You've traveled through the layers of reality, from the largest scales to the smallest, and now it's time to rest. Let go of these thoughts now. Let them drift away like clouds dispersing in the sky. You don't need to understand everything. You don't need to solve the mysteries. The universe will keep its secrets a little longer, and that's okay. You've touched something profound tonight, contemplated the deep structure of existence, and that's enough. Feel your body relaxing completely. Feel the bed supporting you, the layers of reality supporting you at every scale. Feel your breathing becoming slower and deeper, your heartbeat steady and calm. Feel your mind quieting, thoughts becoming less frequent, consciousness beginning to fade as sleep approaches. The layers of reality will still be there tomorrow. The planets will still orbit, the stars will still shine, the quantum fields will still fluctuate, the universe will still expand. None of it depends on your awareness. It all continues whether you're awake or asleep, whether you're thinking about it or not. And that's comforting in a way. You can rest knowing that the cosmos is vast and ancient and will persist, that you're part of something much larger than yourself, something that holds you and supports you at every level. So rest now. Let the brown noise wash over you. Let it carry you into deep, peaceful sleep. Let everything go. Let the layers fade from awareness. Let there be only darkness and quiet and the gentle descent into sleep. You are safe. You are held by reality at every layer, from the quantum foam to the cosmic expansion, from the solid earth to the vast galaxy. You're part of the pattern, part of the dance, a brief but beautiful expression of the universe's complexity. And right now, your part is simply to rest, to sleep, to let your body and mind recover and renew. Sleep deeply now. The brown noise will continue through the night, a constant companion, keeping you in restful slumber. And when you wake in the morning, you'll carry with you the memory of this journey, this exploration of the layers of reality, this glimpse into the deep structure of everything that is. Good night. Rest well, and may you dream of the cosmos in all its layered, mysterious, beautiful glory.